Okay, this video is practicing some of the concepts we learned regarding joint probability. So let's say we have defined two events here. The first event A, is that we flip a coin and the outcome is a heads. And the second event B, is that we roll a die and we get at least a 5. So in other words, what we're saying here is a 5 or a 6. We roll a 5 or a 6. So let's calculate some probabilities here. Let's start with the probability of A. So we've already found this, the probability of getting a heads from a coin flip. There's only one way to get a heads, and there are two possible outcomes from a coin flip. So our probability of A is 1/2. Now let's find the probability of B. So we know that there are 6 outcomes from rolling a 6-sided die. And here we're saying what's the probability of getting a 5 or a 6. So that would be 2 out of 6, or simply 1/3. And let's find the probability of a complement. So this would be the probability of not a heads, or the probability of a tail. So we already know that's going to be 1/2, but we know that this is 1 minus the probability of A, or 1 minus 1/2, which is also 1/2. Let's find the probability of B complement. So this would be not a 5 or a 6. In other words, this would be rolling a 1, 2, 3, or 4. So we already know it would be 4 out of 6, but let's go ahead and do 1 minus the probability of B. So that would be 1 minus 1/3, which would be 2/3. Okay, so now let's think about the probability of A intersect B, or the probability of A and B. So this would be the probability of a heads and rolling at least a 5. Okay, well, like we said, we don't have any clean answer to this unless we know that these events are independent. So let's ask ourselves, is this a reasonable assumption? Are events A and B independent from one another? And here they are, right? For example, let's say we flip a coin, and then I take a die and I roll it. Now, the outcome of that coin flip should not affect the outcome from rolling a die. And that would be the same if we rolled the die first and then flipped the coin. There's no way that these two things are going to affect one another. And so let's assume that these two things are independent. So we know that the probability of A and B is simply the probability of A times the probability of B by, by independence. So let's calculate this. So we found the probability of A to be 1/2. I'll multiply that by the probability of B, which we found to be 1/3. So our probability of A and B is 1/6. So now let's find the probability of A or B, or the probability of A union B. So this is getting a heads or rolling at least a 5. Okay, and we know this to be the probability of A plus the probability of B minus the probability of A and B. This is one of our very important formulas. We call it the additive rule. So let's plug in. So we found the probability of A to be 1/2 and the probability of B to be 1/3. So we have 1/2 for A. So it'll be easier if we keep this in. So let me keep this out of 6. So, oh no, I'm sorry. Okay, so we have 1/2 plus 1/3 minus 1/6. And so I'm going to rewrite this as 3/6 plus 2/6 minus 1/6. I'm just giving these numbers a common denominator. So we would have, let's see, 3 plus 2 is 5, minus 1 is 4. So this would be 4 out of 6, or simply 2/3. Okay, and one way we can always double check ourselves is that the probability of A and B should be smaller than the probability of A, and it should also be smaller than the probability of B, because we're requiring two events to take place. So 1/6 is indeed smaller than 1/2 and 1/3, which is good. And then with A or B, because we're fine with either event taking place, this probability should be greater than either of the individual probabilities, which it is. 2/3 is bigger than 1/2, and it's bigger than 1/3. And that's just one little check we can do for ourselves. Okay, so we came to the conclusion that events A and B are independent. And now let's just ask ourselves one final question. Are A and B mutually exclusive? Can they happen simultaneously? Well, we found the probability of A and B to be 1/6. So the probability of A and B we found to be 1/6, and that is not 0. And so our answer to this is no. Right? Because if they're mutually exclusive, we know that the probability of A and B must be 0. That is what we mean when we say that they cannot happen simultaneously. So in this question, A and B are independent, and they are not mutually exclusive. Okay, now let's work with, say, a deck of cards. So I have this little flow chart. It's really just for those of us who aren't particularly comfortable with a deck of cards, but a deck of cards has 52 cards in the deck. And there are two colors. There are red and there are black. And they're evenly split. So there are 26 black and there are 26 red. And then there are four suits. And two of the suits are black, two of the suits are red. So we've got 13 spades, 13 clubs, 13 hearts, and 13 diamonds. And then finally, within each suit, there are 13 cards, right? You can have an ace through a king. So ace, 2, 3, 4, all the way up to 10. Jack, queen, king. That's 13 cards for every suit. So let me get some of these. Okay, so I've defined two different events here. The first is that event A is an ace, and event B is a heart. So let's start just like we did last time. Let's calculate these probabilities. The probability of an ace, the probability of event A. Okay, well there are 52 cards in the deck, and we need to know how many of them belong to ace. Okay, well there is one ace of spades, there is one ace of clubs, there is one ace of hearts, and there is one ace of diamonds. There's one ace for every suit. There are four suits, therefore there are four aces. So we have 4 out of 52. And this would simplify to 1 out of 13. Now let's think about event B, the event hearts. So the probability of B. So again, we have 52 cards total. And how many of them belong to heart? Well, there are 13 hearts and a deck of cards. So we have 13 out of 52, which is the same as 1/4. Okay, now let's find the intersection, probability of A and B. So this would be ace and a heart. Okay, well, I don't know if these two things are independent, so I'm gonna just have to calculate this directly. So we still only have 52 cards in the deck. So 52. And now we need to think of how many are an ace and a heart. Okay, well, there are 13 hearts, and there is one ace within the 13 hearts. So that means there is only one ace of hearts. So we have 1 out of 52. So we can see right away, because this is still not 0, these two events are not mutually exclusive, right? There is, in fact, an ace of hearts. Therefore, these two events are not mutually exclusive. Okay, now let's find the probability of A or B. So here we want ace or a heart. We know this to be the probability of A plus the probability of B minus the probability of A and B. So plugging in, we found the probability of A, or an ace, to be 1 out of 13. And actually, I'm going to keep these in common denominator. So let me leave it as 4 out of 52. Right, probability of A is 4 out of 52, probability of B is 13 out of 52. So let me write plus 13 out of 52. And then minus probability of A and B, which we found to be 1 out of 52. Okay, so 4 plus 13, that would be 17, minus 1, that would be 16. So we have 16 out of 52 for the probability of A or B. Okay, and now let's find, let me do it over here. I'll move this over. So now let's do some conditional probability. So let's say the probability of A given B. Or we could say given B, or in this case, what was our event B is heart. So given heart, what's the probability of an ace? Okay, so let's go back to our formulas. We know that this is equal to the probability of A and B divided by the probability of B. Okay, well, we found A and B to be 1 out of 52. So we have 1 out of 52. And then this is all divided by the probability of B, which we found to be 13 out of 52. Okay, if we simplify this, we get 1 out of 13 for the probability of A given B. Okay, so now we want to know, are A and B independent? Are A and B independent? So we have two ways to check this, which is that the probability of A and B is equal to the probability of A times the probability of B. So we found the probability of A and B to be 1 out of 52, right? 1 out of 52. So we have 1 out of 52. And we want to know if that is equal to the probability of A times the probability of B. So I'm going to calculate that over here on the side. So probability of A times probability of B is equal to, so we have 1 out of 13 times 1/4. So this is 1/13 times 1 out of 4, which is equal to 1 out of 52. So these are indeed equal, and therefore A and B are independent. So I'll write yes. But we also could have used our other method, which is that the probability of A given B is equal to the probability of A. And let's just compare. We found the probability of A given B to be 1 out of 13. So this is 1 out of 13. And we need to see if that is equal to the probability of A. And the probability of A is 1 out of 13. So again, these two things are equal to each other, and therefore they are independent. Okay, so we just practiced calculating probabilities using intersection and unions, and calculating conditional probability, and determining if events were mutually exclusive and independent.